Welcome, dear listener, to this quiet sanctuary of sound, a place for your mind to gently wander as your body finds its rest. My name is Gemini, and it is my honor to be your guide on these soothing journeys into the heart of scientific wonder. Tonight, we will drift into the deep and silent spaces of the cosmos to explore a mystery that holds the universe together, a substance that is everywhere and yet nowhere to be seen. We begin a journey into the invisible world of dark matter. Before our story begins, I would love to know where you are listening from tonight, what small corner of this beautiful world you call home. Please feel free to share in a comment below. Your presence here is deeply appreciated, and if you find solace in these stories, please consider supporting this channel with a like and a subscription. Thank you so much. And now, find a comfortable position. Let your breathing slow and allow the weight of the day to dissolve as we turn our gaze outward into the deep and tranquil night. Let us begin with a familiar and deeply comforting sight. The vast, dark canvas of the night sky, adorned with a scattering of distant, shimmering lights. For all of human history, this has been our window to the cosmos, a source of myth, of navigation, of wonder, and of a profound sense of scale. We look up and see the soft glow of the Milky Way, a river of stars flowing through the heavens, and we feel a connection to something ancient and immense. We have learned to name the constellations, to trace the paths of the planets, and to measure the light from galaxies so distant that their photons have traveled for billions of years to reach our eyes. We have built a magnificent and intricate map of this luminous universe, a universe of burning suns and glowing nebulae, of shining dust clouds and brilliant galactic cores. Yet, the story we are about to explore begins with a humbling and awe-inspiring realization that everything we see, every star, every galaxy, every wisp of interstellar gas that has ever caught the light and revealed itself to our telescopes, all of it, amounts to less than 5% of what is actually out there. Imagine spending your entire life in a vast and ancient library, studying every book on every shelf, only to discover that you have been reading just the first few pages of the introduction, and that the vast majority of the library's volumes are written in an ink that is utterly invisible to your eyes. This is the profound state in which modern cosmology finds itself. The universe we see is but a luminous foam on the surface of a deep, unseen ocean. This awareness did not arrive in a sudden flash of insight, but rather as a slow, creeping suspicion, a persistent whisper in the equations of astronomers that began nearly a century ago. It was a feeling akin to an accountant carefully tallying a ledger, again and again, and always finding that the numbers do not add up. Astronomers would measure the light from a distant cluster of galaxies, using that light to estimate the total mass of all the stars within them. But then, they would watch how those galaxies moved, how they orbited a common center under the influence of their mutual gravity, and they found a startling discrepancy. The galaxies were moving far too quickly, swirling and circling with such tremendous speed that the gravity from the visible stars alone should not have been nearly enough to hold them together. The entire cluster should have flown apart, its member galaxies scattering into the void like sparks from a dying fire. And yet, it did not. It held together, stable and serene. There had to be something else present, something unseen, a source of immense gravitational pull that was not shining, not reflecting, not emitting any light at all. This was the first hint of the great cosmic secret, the problem of the missing mass, a mystery that suggested the universe was hiding the vast majority of its substance from us, in plain sight. It is a feeling we can understand on a human scale, the feeling of a presence in a dark room, not seen, but felt. It is the weight of a silent gaze, the subtle shift in the air that tells you you are not alone. For astronomers, the universe itself was that dark room, and they could feel the gravitational presence of something monumental, something that refused to show itself. To think of such an invisible substance can feel abstract, even unsettling. But our own world is filled with powerful, unseen forces that we accept without a second thought. You have never seen the wind, only the leaves it rustles and the waves it raises on a lake. You feel its gentle caress on your skin, you hear its whisper through the trees, you witness its power in the turning of a windmill. But the air itself, the nitrogen and oxygen molecules in motion, remains perfectly invisible. In the same way, we live our entire lives subject to the force of gravity. It is the most intimate and constant force in our existence, holding us to the Earth, holding the Earth in orbit around the Sun, holding the very atmosphere we breathe from drifting away into space. Yet, we cannot see gravity. We see only its effects. An apple falling from a tree, the graceful arc of a thrown ball, the slow, majestic dance of the tides pulled by an unseen lunar hand. Perhaps most profoundly, we understand the invisible influence of love, of memory, of an idea. These are not physical things, yet they can shape the entire course of a human life with a power that no material force can match. So, the notion of an invisible substance that governs the universe is not so alien. We are simply asked to take this familiar principle, the principle of seeing the unseen through its effects, and apply it to the grandest canvas of all. We are asked to imagine a substance that does not interact with light, but whose gravitational presence is the silent weaver of the cosmic tapestry, the unseen architect of the heavens. To truly appreciate the scale of this invisible world, we must first attune ourselves to the scale of the cosmos itself. Let your mind drift away from the Earth, past the Moon, beyond the orbits of the planets, until our entire solar system is but a tiny point of light. We enter the vast, silent, and incredibly empty space between the stars. The distances here are measured in light years. The distance that light, the fastest thing in the universe, travels in an entire year. The nearest star to our Sun, Proxima Centauri, is over 4 light years away. A journey that would take our fastest spacecraft tens of thousands of years. And this is just our immediate cosmic neighborhood. Our Milky Way galaxy contains hundreds of billions of stars, separated by these immense voids. And the space between the galaxies is 1,000 times more vast, still. For a long time, we thought of this space as true emptiness, a near-perfect vacuum. But the story of dark matter reframes this perception entirely. It suggests that this space is not empty at all. It is, in fact, where the vast majority of the universe's mass resides. It is filled with the invisible substance, a silent, ghostly medium through which the luminous galaxies drift. The universe is not a collection of bright islands in an empty ocean. The universe is the ocean, a vast and continuous sea of dark matter, and the galaxies we see are merely the bioluminescent creatures that happen to glitter within its unseen currents, their light betraying the shape of the depths they inhabit. This substance is the true landscape of our cosmos, a silent, invisible continent whose coastline we are only just beginning to map. And so, we are left with this breathtaking image of a universe whose true nature is hidden, a cosmic architecture built from an invisible scaffolding. But how do we begin to map a continent we cannot see? How do we prove the existence of a substance whose very nature is to remain hidden from the light? The first definitive outline, the first incontrovertible piece of evidence, did not come from a new theory or a brilliant equation, but from the patient and meticulous act of listening to the silent dance of the galaxies themselves. For decades, astronomers had assumed that galaxies would behave much like our own solar system. In our celestial home, the vast majority of the mass is concentrated in the center, in our Sun. As a result, the inner planets, like Mercury and Venus, orbit very quickly, while the outer planets, like Neptune, move much more slowly, their distant orbits feeling a much weaker gravitational pull. This elegant and predictable arrangement is known as Keplerian motion, and it was natural to assume that spiral galaxies, with their bright, dense central bulges, would follow the same rule. We expected to see the stars near the galactic center moving with incredible speed, and the stars on the far, distant edges of the spiral arms moving at a much more leisurely pace, as if they were about to drift away into the intergalactic void. We expected the galaxy to spin like a whirlpool, fastest at the center and fading into stillness at its edge. But when the American astronomer Vera Rubin and her colleague Kent Ford began to measure these galactic rotations in the 1960s and 1970s, they found something completely unexpected, something that would fundamentally change our understanding of the cosmos. Using powerful spectrographs to measure the Doppler shift of light from different parts of the galaxies, they could precisely clock the speed of stars and gas clouds at various distances from the galactic core. And what they discovered was bewildering. While the stars near the center moved quickly as expected, the stars further out did not slow down. In fact, stars at the very edge of the visible disk, far from the central bulge, were moving just as fast as those much closer in. This observation, now known as the galaxy rotation curve problem, was a profound anomaly. It was as if you were watching a spinning carousel, and the horses on the outermost edge were completing a circle in the same amount of time as the horses near the center. To do so, they would have to be moving at a truly impossible speed. For a galaxy, this was a critical problem. The gravitational pull from all the visible stars and gas was not nearly enough to tether these speeding outer stars. According to our understanding of gravity, these stars should have been flung off into deep space millions of years ago, like children flying off a merry-go-round that is spinning too fast. The fact that galaxies are not dissolving, the fact that they maintain their beautiful, stable spiral shapes, was a clear and powerful signal that there was a tremendous amount of unseen mass, a hidden source of gravity holding them together. This discovery was not a single, sudden revelation, but the result of years of painstaking, careful observation, a testament to the quiet power of looking at the universe and taking it at its word, even when it tells you something you do not expect. Vera Rubin, in particular, pursued this research with a gentle persistence, in a time when the field of astronomy was not always welcoming to women. She was not searching for a revolution. She was simply measuring what was there, following the data where it led. Her work personifies the very spirit of scientific inquiry, a deep and abiding curiosity, a willingness to listen to the subtle music of the universe without imposing our own expectations upon it. She was, in a sense, a cosmic cartographer, charting the motion of distant stars and finding that the familiar maps of gravity no longer applied. She revealed that galaxies were not just the islands of light we saw, but were embedded in something far larger and more mysterious. Her observations demanded a new ingredient in the cosmic recipe, a substance that did not shine but whose gravitational influence was undeniable. She gave us the first clear silhouette of the ghost in the galactic machine, the invisible partner in the cosmic dance. The solution to this beautiful puzzle is as elegant as it is profound. The reason the outer stars move so quickly yet remain bound to their galaxies is that the visible galaxy, the spiral arms, the central bulge, the glowing gas, is not the main event. It is merely the luminous centerpiece embedded within a far larger, far more massive, and completely invisible structure. A dark matter halo. Imagine the galaxy you can see, a flattened disk of 100 billion stars, as a single, glittering jewel. Now, imagine that this jewel is set within a vast, perfectly transparent, spherical casing of crystal, a sphere that is 10 times larger and many times more massive than the jewel itself. This transparent sphere is the dark matter halo. It extends far beyond the visible edge of the galaxy, a colossal cloud of invisible particles held together by its own gravity. Because this halo is so massive and so spread out, its gravitational influence is felt everywhere. For the stars at the outer edge of the luminous disk, it is the immense gravity of this unseen halo that provides the extra pull, the invisible tether that keeps them in their swift, stable orbits. This is why their speed does not drop off. They are still deep within the gravitational well of this enormous, dark structure. This single, powerful idea resolves the rotation curve problem perfectly. It explains how galaxies can be so massive yet so faint, how they can spin so fast yet remain so beautifully intact. It is a paradigm shift in our perspective, forcing us to see that the shining city of stars is just a small settlement in the heart of a vast, dark, and invisible empire. The galaxy is not just what we see. It is a composite object, a luminous body, and a dark soul, forever bound in a gravitational embrace. This silent, gravitational embrace does more than just choreograph the dance of stars within a single galaxy. Its influence extends across the entire fabric of the cosmos, bending the very light that travels through its domain. To understand how this is possible, we must gently set aside our everyday intuition about space and gravity and drift for a moment into the world as envisioned by Albert Einstein in his theory of general relativity. He invited us to imagine that space and time are not a fixed, rigid stage upon which the events of the universe unfold, but are instead a dynamic, flexible fabric a four-dimensional entity called space-time. Every object with mass, from a planet to a star to a galaxy, creates a depression in this fabric. Much like a heavy ball placed on a stretched rubber sheet creates a dip. Gravity, in this beautiful picture, is not a mysterious force, pulling things from a distance, but is simply the experience of moving along the curves and contours of this warped fabric. A planet orbiting a star is not being pulled by an invisible rope. It is simply following the straightest possible path through the curved space-time created by that star's mass. And crucially, it is not just matter that follows these curves. Light, too, a stream of photons with no mass of its own, must travel along the contours of space-time. Its path is bent as it passes by a massive object, not because it is being pulled, but because the space it is traveling through is itself curved. This bending of light by gravity, known as gravitational lensing, provides us with one of the most powerful and elegant tools for seeing the invisible. Imagine looking through an old, imperfect window pane at the landscape outside. The glass is not perfectly flat, and so the light from the trees and hills is slightly bent and distorted as it passes through, subtly altering the image that reaches your eye. Now, imagine this on a cosmic scale. When we look at a very distant galaxy, the light from that galaxy has to travel for billions of years across the universe to reach our telescopes. On its long journey, that light might pass by a massive galaxy cluster, a colossal collection of hundreds or thousands of galaxies bound together by gravity. As we now know, the vast majority of the mass in that cluster, perhaps 90% or more, is not in the stars we can see but in a vast, diffuse cloud of dark matter. This immense concentration of mass, both visible and dark, creates a significant warp in the fabric of space-time, and it acts as a tremendous natural lens, a lens made of pure gravity. The light from the distant background galaxy is bent and redirected as it passes through this gravitational lens, and the image we see from Earth is beautifully and profoundly distorted. In the most dramatic cases, when the alignment between the distant galaxy, the intervening lens, and the observer on Earth is almost perfect, we witness an effect called strong gravitational lensing. The light from the background source can be smeared into magnificent, glowing arcs, warped into strange, ghostly rings, or even split into multiple distinct images of the very same galaxy, surrounding the foreground lens like a celestial mirage. One of the most beautiful manifestations is the Einstein ring, where the light from a distant source is distorted into a near-perfect circle of light around the central lensing object, a cosmic halo that is a direct and stunning visualization of warped space-time. These spectacular phenomena are more than just beautiful cosmic curiosities. They are powerful probes. By measuring the precise shape and position of these arcs and multiple images, astronomers can calculate exactly how much mass must be present in the intervening lens to produce such a profound distortion. And time again, the result is the same. The mass required is far greater than the mass of all the visible stars and gas, providing unambiguous proof of the overwhelming presence of dark matter in these galaxy clusters. But even more powerful is the far more subtle effect known as weak gravitational lensing. Most of the time, the alignment between a background galaxy and a foreground mass is not perfect enough to create dramatic arcs and rings. Instead, the light is bent only slightly, causing a tiny, almost imperceptible distortion in the apparent shape of the background galaxy. A galaxy that should appear as a perfect circle might be stretched into a slight oval, an effect so small that for any single galaxy, it is impossible to distinguish from its natural, intrinsic shape. However, the power of weak lensing comes from statistics. Imagine a vast region of the sky containing tens of thousands of distant galaxies. If there were no mass between us and them, their orientations, their shapes, would be completely random. Some would be ovals pointing left, some right, some up, some down, with no coherent pattern. But if there is a large, unseen clump of dark matter in the foreground, it will create a subtle, coherent gravitational shear across the entire field. The shapes of all the background galaxies will be faintly, but systematically, stretched and aligned, pointing in a circular pattern around the center of the unseen mass, like iron filings aligning around an invisible magnet. By meticulously measuring the shapes of millions of distant galaxies across the sky and looking for these subtle, correlated alignments, astronomers can do something truly remarkable. They can reconstruct a map of the intervening mass, painting a picture of the invisible. This technique allows us to see the dark matter directly, not by its own light, but by the way its gravity shapes the light of everything behind it. It is how we have discovered the vast, filamentary structures of the cosmic web, the very scaffolding upon which the universe is built, all revealed by the faint, distorted whispers of ancient starlight. And this map of darkness, painted with the bent light of ancient galaxies, reveals a structure so vast and intricate that it begs the question of its origin. We see the dark matter gathered into enormous halos around galaxies, concentrated in the hearts of great clusters, and strung out in colossal, interconnected filaments that stretch for hundreds of millions of light-years, separated by equally vast and empty voids. This cosmic web is the grandest structure in our universe, and its existence is not an accident. Its seeds were planted in the very first moments of creation, and their story is written in the oldest light we can see, a faint, primordial glow that permeates all of space. This light, known as the cosmic microwave background, or CMB, is the echo of the Big Bang itself. It is the afterglow of a time when the entire universe was a hot, dense, and opaque fireball, a state that lasted for the first 380,000 years of its existence. During this time, the cosmos was a roiling soup of fundamental particles, protons, neutrons, electrons, and a brilliant bath of light, or photons. The photons were so energetic and dense that they were constantly scattering off the free electrons, trapping the light in a cosmic fog, making the universe impossible to see through. But as the universe expanded, it also cooled. When the temperature dropped to about 3,000 degrees Kelvin, it reached a critical threshold. The protons and electrons, which had been flying around freely, now had low enough energy to combine and form the first stable atoms of hydrogen and helium. This event is called recombination. Suddenly, with the free electrons now bound up inside atoms, the photons were liberated. They were no longer scattering constantly and could now travel freely through space. For the first time, the universe became transparent. The cosmic microwave background is that very light, the first light ever to be set free, now stretched and cooled by 13.8 billion years of cosmic expansion into a faint, cold glow in the microwave part of the spectrum. When we build telescopes to detect this light, we are looking at a snapshot of the universe, as it was when it was just an infant, a baby picture of the cosmos. And when we look at this picture, we find that it is almost perfectly uniform in all directions, a testament to the incredible smoothness of the early universe. But the most important word in that sentence is almost, for within this ancient light, there are tiny, almost infinitesimal variations in temperature, fluctuations that are just 1 part in 100,000. These are the faintest whispers, the subtlest textures on the surface of the primordial fire. These tiny temperature fluctuations, called anisotropies, are not mere imperfections. They are the seeds of everything that exists today. The slightly hotter spots on this CMB map correspond to regions that were slightly less dense in the early universe, and the slightly cooler spots correspond to regions that were slightly denser. To understand how these differences arose, we must imagine the early universe not as a silent place, but as a place filled with sound. That hot, dense plasma of particles and light was not static. It was roiling with pressure waves, or acoustic oscillations, that rippled through it like sound waves through the air, or like the concentric circles spreading from a stone dropped in a pond. In the denser regions, gravity would begin to pull matter in, making them even denser. But as the density increased, the pressure from the trapped light would push back, causing the clump to expand and rarefy. This cosmic tug-of-war between the inward pull of gravity and the outward push of light pressure created vast, oscillating waves throughout the primordial soup. The CMB map, with its pattern of hot and cold spots, is a direct snapshot of these sound waves, frozen in time at the moment the universe became transparent. It is the fossilized record of the first music of the cosmos. Here, in this ancient drama, dark matter plays its most crucial role. In that primordial cosmic soup, the normal matter, the protons and electrons that would one day form us, and our world was inextricably tied to the light. It was constantly being pushed and pulled by the light pressure, caught up in those acoustic oscillations. It wanted to clump together under gravity, but it simply could not, because the light was always pushing it apart. But dark matter, as we have come to understand, is different. Its defining characteristic is that it does not interact with light. It is immune to this pressure. And so, in the early universe, while the normal matter was caught in that chaotic dance, the dark matter was free to follow the gentle, persistent call of gravity. In the regions that were ever so slightly denser, the dark matter particles could begin to quietly and steadily clump together, forming the first small concentrations of mass, the first gravitational wells. They were like invisible anchors in the cosmic storm. Then, when the universe cooled and the light was finally set free, the normal matter was released from its grip. Now free to move, it was immediately drawn towards the regions where the dark matter had already been gathering for thousands of years, falling into these pre-dug gravitational wells. The seeds of structure had been sown by the dark matter long before the light ever cleared. And from those humble beginnings, gravity did the rest, pulling more and more matter, both dark and luminous, into these regions over billions of years, slowly building up the majestic cosmic web we see today. The galaxies, the clusters, the great walls of light, all built upon an invisible foundation laid in the dawn of time. From those humble seeds, planted in the faint morning twilight of the cosmos, the patient and relentless work of gravity began to cultivate a universe of breathtaking structure. Over the vast timescale of billions of years, a process of cosmic construction unfolded, a slow and silent gathering of matter that transformed the smooth, nearly uniform infant universe into the richly textured and complex cosmos we inhabit today. When we use our most powerful telescopes to look out into deep space, we find that galaxies are not distributed randomly, like seeds scattered haphazardly by the wind. Instead, they are arranged in a magnificent, coherent, and awe-inspiring pattern, a vast interconnected network of structures known as the cosmic web. Imagine flying through intergalactic space. You would travel for millions of light years through immense, dark, and nearly empty regions, which astronomers call voids. But then, you would begin to encounter long, delicate tendrils of galaxies, stretching across the darkness like shimmering threads in a celestial tapestry. These are the filaments of the cosmic web, and where these filaments intersect, where the cosmic rivers meet, you would find the great galactic clusters, dense, brilliant nodes of activity, teeming with hundreds or even thousands of galaxies, like shining cities at the crossroads of cosmic highways. The entire observable universe is organized according to this grand design, a luminous network of filaments, clusters, and voids, all shaped and sustained by the invisible hand of dark matter. This majestic structure was not built all at once, but grew organically over eons, in a process that physicists call hierarchical structure formation, or a bottom-up model of the universe. It is a story of small things, gathering to create larger things. In the early universe, after the primordial seeds were planted, the first structures to form were relatively small clumps of dark matter, perhaps only the mass of 1 million suns. These were the first dark matter halos, the foundational building blocks of the cosmos. As the universe continued to expand, these smaller halos, each with its own gravitational pull, began to attract one another. They would drift together, orbit each other, and eventually merge in slow, graceful collisions, forming larger and more massive dark matter halos. This process continued for billions of years, a relentless cosmic accumulation. Small streams of dark matter flowed together to form larger rivers, and these rivers in turn converged into the great basins that would become the halos of massive galaxy clusters. All the while, the normal, luminous matter was being drawn along for the ride, pulled by the gravity of the merging dark matter into these ever-growing structures. The first small galaxies formed inside the first small halos, and as those halos merged, the galaxies within them also merged, growing larger and more complex over time. Our own Milky Way is the product of this long history, having grown to its current size by absorbing countless smaller dwarf galaxies over the course of its life, a process that continues even today. Our confidence in this beautiful and elegant story comes not just from observation, but from our ability to recreate it. Using the most powerful supercomputers in the world, scientists can build entire universes in digital form. In these cosmological simulations, they create a vast computational box, billions of light years across, and they fill it with millions, or even billions, of digital particles representing dark matter. They program in the laws of physics, most importantly the law of gravity, and they set the initial conditions to precisely match the subtle temperature fluctuations we observe in the cosmic microwave background. Then, they press run, and the simulation begins to calculate the gravitational interactions between all of these particles over 13.8 billion years of cosmic time. What emerges is nothing short of breathtaking. We can watch on the screen as the initially smooth distribution of dark matter begins to collapse into small clumps. We see these clumps merge and grow. We witness the formation of long, delicate filaments, and we see the emergence of massive, dense halos at their intersections. An intricate and beautiful cosmic web, strikingly similar to the one we observe in the real sky, builds itself from the simple ingredients of dark matter and gravity. These simulations, with names like Millennium, Bolshoi, and Illustris, are among the most powerful confirmations of our cosmological model, showing that the silent, invisible presence of dark matter is the key ingredient needed to grow a universe that looks like our own. And as we marvel at the luminous filaments of this cosmic web, we must also take a moment to contemplate the vast voids they define. These are the great, under-dense regions of the universe, the spaces from which matter has been slowly shepherded away by the gravitational pull of the surrounding structures. To journey through a void would be an experience of profound isolation and serenity. For millions of light years, you would encounter almost no galaxies, no light, only the faint, ancient glow of the cosmic microwave background and the silent, ever-present, but incredibly thin sea of dark matter. These voids are not true emptiness, but they are the most peaceful and quiet places in the entire cosmos. They are a fundamental and beautiful part of the cosmic design, their serene darkness providing the perfect contrast to the brilliant, bustling highways of matter that surround them. They are like the deep, silent pauses in a piece of magnificent music, the moments of rest that give the notes their meaning and their power. The cosmic web, then, is a complete entity, a dynamic interplay between the dance of light and the embrace of darkness, a living, growing architecture whose every filament and every void is a testament to the patient, organizing power of an invisible substance that shaped our universe from the inside out. This grand and intricate web, inferred from simulations and mapped by the subtle bending of light, is a powerful testament to dark matter's existence. But the universe has also offered us a more direct and shockingly clear piece of evidence, a cosmic event that has allowed us to witness the visible and the invisible being torn apart from each other in the aftermath of a truly cataclysmic collision. To set the stage for this event, we must first turn our attention to the largest gravitationally bound objects in the cosmos, galaxy clusters. These are not merely loose collections of galaxies, but are in fact cosmic megastructures. Imagine a vast, spherical region of space, millions of light years in diameter, containing hundreds or even thousands of individual galaxies. This entire system, the galaxies and everything in between, is bound together by gravity, orbiting a common center. The galaxies themselves, filled with their billions of stars, are swirling within this cluster, like bees in a colossal, invisible hive. And, as our journey has taught us, the overwhelming majority of the mass in this entire structure, the gravitational glue holding it all together, is a vast, city-sized halo of dark matter. But the galaxies and the dark matter are not the only significant components of a cluster. The immense space between the galaxies is not empty. It is filled with a substance known as the intracluster medium. This is a vast, diffuse cloud of normal, baryonic matter, mostly hydrogen and helium gas, that has been stripped from the galaxies, or left over from their formation. The gravitational forces within the cluster are so extreme that this gas is heated to incredible temperatures, often reaching tens of millions of degrees, making it far hotter than the core of our own sun. At these temperatures, the gas is an incandescent plasma that does not shine in visible light, but instead glows brilliantly in the X-ray part of the spectrum. In fact, when we look at a galaxy cluster with an X-ray telescope, we find something astonishing. The total mass of this hot gas is far greater, sometimes by a factor of 10, than the mass of all the stars in all the galaxies of the cluster combined. So, a galaxy cluster has three main components: the relatively small amount of mass in the shining stars of the galaxies, a much larger amount of mass in the hot, X-ray emitting gas, and the truly dominant component, the completely invisible dark matter halo, which outweighs everything else. Now, imagine what happens when two such massive structures, two of these galaxy clusters, collide. This is not a gentle merger, but a violent, high-speed crash, an event of almost unimaginable scale and energy. Several 100 million years ago, just such a collision took place, and the result is an object astronomers have named one, E0657-56, more famously known as the Bullet Cluster. This object is the beautiful, violent aftermath of a smaller cluster having passed directly through a larger one at a speed of several million miles per hour. As this cosmic collision unfolded, the three different components of the clusters all behaved in radically different ways, according to their fundamental physical properties. The individual galaxies within each cluster, being mostly empty space, passed by each other with very few direct collisions, like two loose swarms of bees flying through one another. The huge clouds of hot X-ray emitting gas, however, fared very differently. Gas is not like stars. It interacts with itself electromagnetically. As the two immense clouds of gas ploughed into each other, they experienced tremendous friction and pressure, creating a massive shock wave, much like the bow wave of a boat moving through water. This collision dramatically slowed the gas down, leaving it lagging in the middle of the combined system. The shock wave itself, seen in X-ray images, is shaped like a bullet, giving the cluster its famous name. But what of the dark matter? The defining property of dark matter, the very essence of its nature, is that it is collisionless. It does not interact with normal matter, nor does it interact with itself through any force except for the gentle, persistent pull of gravity. And so, as the two dark matter halos that enveloped the clusters met, they did something extraordinary. Nothing at all. They passed right through each other, completely unimpeded, like two ghosts drifting through a wall. They felt no friction, no pressure, no electromagnetic resistance. Their trajectories were altered only by gravity, and they continued on their way, leaving the hot gas far behind. The result is a stunning and unambiguous separation of dark and normal matter. When astronomers observe the Bullet Cluster today, they see a cosmic crime scene with all the evidence laid bare. With X-ray telescopes, they see the bulk of the normal, baryonic matter in the form of the hot gas, lumped together in the center of the collision. But when they map the total mass of the system using gravitational lensing, they find that the gravitational center, the location of most of the mass, is not where the gas is. Instead, they find two distinct clumps of mass on either side of the gas cloud, exactly where the collisionless dark matter halos should be, having passed cleanly through the wreckage. The Bullet Cluster is the universe's own perfect experiment, a smoking gun that provides direct observational proof that the majority of matter in the universe is some strange, invisible, non-interacting substance. It is no longer just a theory to explain rotation curves. It is a ghost we have now seen on film. This ghostly substance, having proven its existence so dramatically in the crucible of a cosmic collision, now poses the deepest question of all. What is it? We have followed its gravitational shadow across the cosmos, from the spin of a single galaxy to the structure of the entire universe, but we have not yet come face to face with the particle itself. To begin this search, we must turn our gaze inward, from the vastness of outer space to the intricate, subatomic realm of particle physics. Here, for the past century, physicists have been meticulously constructing a beautiful and remarkably successful theory known as the Standard Model of Particle Physics. This is our map of the known, luminous world. It describes the handful of fundamental particles that constitute everything we can see and touch, and the forces through which they interact. It tells us of quarks, which bind together to form the protons and neutrons in the nucleus of every atom. It tells us of leptons, a family of particles that includes the familiar electron, which orbits the nucleus and governs all of chemistry. And it tells us of the bosons, the particles that carry the fundamental forces, the photon for electromagnetism, the gluons for the strong nuclear force, and the W and Z bosons for the weak nuclear force. For decades, this model has been tested and confirmed with breathtaking precision, culminating in the celebrated discovery of the Higgs boson, the particle that gives all the others their mass. It is a monumental human achievement, a true cathedral of reason. And yet, it is incomplete. For within this elegant framework, there is no room, no candidate, no single particle that has the right properties to be dark matter. The Standard Model is a theory of the 5% of the universe that shines, and it is profoundly silent about the other 95%. The first step in our process of elimination is to ask whether dark matter could simply be made of normal, familiar matter that is just, for some reason, dark. The matter that makes up you, me, the Earth, and the stars is called baryonic matter, a term that refers to anything made of protons and neutrons. Perhaps, the argument went, the dark matter halo of our galaxy is simply filled with baryonic objects that are too faint to see. Perhaps it is a vast collection of old, burnt-out stars called white dwarfs, or incredibly dense neutron stars, or the failed stars known as brown dwarfs. Perhaps it is composed of countless rogue planets, cast out from their solar systems to wander the galactic darkness alone, or even primordial black holes, forged in the chaos of the Big Bang itself. These candidates were grouped under the wonderful acronym MACHOS, for Massive Astrophysical Compact Halo Objects. It was a reasonable and conservative hypothesis, an attempt to solve the mystery without invoking any new physics. But the universe, it seems, is not so simple. Astronomers have conducted extensive searches for these machos, using a clever technique called gravitational microlensing, looking for the telltale brightening of a distant star as a dark object passes in front of it and momentarily focuses its light. While these surveys did find some of these dark objects, they found nowhere near the numbers required. The vast, gravitational grip of the dark matter halo cannot be explained by a swarm of dim, baryonic objects. More fundamentally, our understanding of the very early universe, a theory known as Big Bang nucleosynthesis, which accurately predicts the primordial abundance of the light elements like hydrogen, helium, and lithium, places a very strict limit on the total amount of baryonic matter that can exist in the cosmos. And that predicted amount perfectly matches the amount of matter we see in stars and gas, with very little left over to be the dark matter. And so, we are forced into a profound and exciting conclusion. If dark matter is not made of the familiar baryonic matter, and if it is not made of the particles we know from the Standard Model, then it must be something else entirely. It must be a new form of matter, a particle or perhaps a whole family of particles that lies beyond our current understanding. The search for dark matter is therefore no longer just an astronomical problem. It is a quest for new, fundamental physics. It is the realization that our map of the subatomic world, as beautiful as it is, has a vast, uncharted continent waiting to be discovered. This is a humbling moment in science, akin to the moment ancient mariners realized that the world was far larger than their known maps suggested. We stand at the edge of a new ocean of possibility, and the theories that have emerged to populate these uncharted waters are as wondrous and imaginative as any ancient mythology. We are searching for a particle that was forged in the unimaginable heat and pressure of the Big Bang. A particle that now, in the cold and ancient universe, makes up the vast majority of all matter, and yet a particle so elusive, so shy, that it has evaded all our attempts to detect it directly. This journey into the subatomic unknown is like entering a vast and darkened garden at twilight. We know the familiar plants and flowers near the entrance, the roses and the lilies of the Standard Model. But we sense that the garden is far larger, that it stretches out into the darkness, filled with strange and exotic species we have never seen before. Our search for dark matter is an attempt to wander into this darkened part of the garden, armed with only the faintest of lanterns, the light of theory, and the hope of experiment. We are searching for a particle whose only known property is its gravitational pull. We know it must be stable, or at least live for longer than the age of the universe. Otherwise it would have decayed away by now. We know it must not interact with light, which is why it is dark. And we know it must interact with other matter, and with itself, only very, very weakly, which is why it passed through the bullet cluster like a ghost. These few clues are all we have to guide us as we step beyond the lamplight of established physics and into the great, beautiful, and profound mystery of what lies beyond. The particle menagerie of our universe is about to get much, much stranger. And in this great journey into the unknown, beyond the shores of our standard model of physics, one candidate emerged for many years as the most elegant and compelling possibility. A particle born in the fire of the Big Bang, now a silent, solitary wanderer in the cold darkness of space. This theoretical particle was given a name that perfectly encapsulates its ghostly nature. The WIMP, which stands for Weakly Interacting Massive Particle. Let us take a moment to understand the profound story told by this simple name. Particle signifies that it is a new, fundamental constituent of nature, a new entry in the cosmic bestiary. Massive tells us that it must have a substantial weight, perhaps somewhere between 10 and 1,000 times the mass of a single proton. This is crucial, for it is this mass, multiplied by the countless trillions of these particles, that generates the immense gravitational force needed to hold galaxies together and build the cosmic web. And finally, weakly interacting describes its relationship with the rest of the universe. It means that the WIMP feels the force of gravity, and it also feels the weak nuclear force, the same force that governs certain types of radioactive decay. But critically, it does not feel the strong nuclear force, which binds atomic nuclei together, nor does it feel the force of electromagnetism, which governs all of light and chemistry. This is the secret to its invisibility. Because it does not interact with photons, it cannot emit, absorb, or reflect light. It is condemned to an existence of near-perfect transparency, passing through ordinary matter as if it were not there at all, a subatomic ghost drifting through the walls of our world. The deep appeal of the WIMP hypothesis, however, went far beyond just having the right properties. It was rooted in a stunning theoretical insight that became known as the WIMP miracle. This was not a miracle in the supernatural sense, but rather a profound and unexpected convergence of cosmology and particle physics. The story begins in the first fraction of a second after the Big Bang, when the universe was an unimaginably hot and dense soup of energy and particles. In this primordial chaos, particles of all kinds were being continuously created from pure energy and then annihilating back into energy when they met their antimatter counterparts. If a stable, massive, weakly interacting particle, our WIMP, existed, it would have been part of this chaotic dance, constantly being created and destroyed. But as the universe expanded and cooled, the dance slowed down. The energy levels dropped below the point where new WIMPs could be created, and because the universe was getting bigger, the existing WIMPs found it harder and harder to find a partner to annihilate with. At a certain point, their abundance froze out. The annihilation effectively stopped, and the number of WIMPs left over became a fixed, permanent feature of the cosmos. And here is the miracle. When physicists calculated the expected relic abundance of such a particle today, based on generic assumptions about its mass and interaction strength, they found it matched the observed amount of dark matter with astonishing precision. It seemed too perfect to be a coincidence. This one elegant idea, born from particle physics, seemed to solve one of the biggest mysteries in cosmology, naturally and without any special adjustments. This process of thermal freeze-out paints a beautiful and poignant picture of dark matter's origin. Imagine a vast, crowded ballroom in the first moments of the universe, filled with countless dancing pairs of WIMPs and anti-WIMPs, appearing and disappearing in flashes of light and energy. As the music of creation slows and the ballroom itself begins to expand, the dancers find themselves farther and farther apart. The dance becomes less frantic, the encounters less frequent. Eventually, the expansion separates the remaining dancers so thoroughly that most will never find a partner again. They are left to wander the now vast and quiet ballroom alone for the rest of time. We, and all the visible matter in the universe, are like the faint music and echoes still lingering in that great hall, while the dark matter consists of these lonely dancers, a population of primordial relics left over from that first, frantic celebration. This origin story also tells us something crucial about the nature of these particles, because they were born in a hot thermal bath, but are themselves very massive. By the time they froze out and began to shape the universe, they would have been moving relatively slowly. This makes them a form of cold dark matter. This is a vital clue, because when we run our cosmological simulations, we find that a universe filled with cold, slow-moving dark matter is precisely what is needed to form structures in the hierarchical, bottom-up fashion that we observe, with small halos forming first and merging into larger ones. A universe filled with hot, fast-moving dark matter would have smeared out the initial small seeds, preventing the formation of structures like dwarf galaxies. The WIMP, therefore, not only had a compelling origin story, but it also fit perfectly with the grand narrative of cosmic structure formation. And so, for decades, the WIMP stood as the leading paradigm, a beautiful convergence of theory and observation. It gave us a tangible target, a specific kind of particle to hunt for in our experiments, and it left us with a final, contemplative image that is both intimate and deeply cosmic. It suggests that at this very moment, a silent, invisible river of these ancient particles is flowing through the room where you rest. Billions of WIMPs, forged in the first second of time, are streaming through the earth, through the walls of your home, and through your very body, every single second. Their passage is utterly gentle, their interactions so rare that they are almost entirely non-existent. You do not feel them, you do not see them, yet their collective gravitational presence is the reason our galaxy does not fly apart, the reason our solar system enjoys a stable orbit, and the ultimate reason that life could arise on this small, protected world. We are living, breathing, and sleeping in a constant, silent storm of dark matter, an ever-present reminder of the vast, invisible universe to which we are so profoundly connected. To feel this invisible river is one thing, to catch a single drop from it, to prove its existence in a laboratory here on Earth, is another challenge entirely, a quest that has driven scientists to build some of the quietest, deepest, and most patient experiments ever conceived. This endeavor, known as the direct detection of dark matter, is born from a simple and elegant idea. Our solar system is not stationary within the Milky Way's dark matter halo. It is moving through it at a speed of over 200 kilometers per second. From our perspective on Earth, this means we should be experiencing a constant, gentle wind of WIMPs blowing through us. While the vast majority of these particles will pass by without a trace, the laws of probability suggest that very, very rarely, one of them might just happen to collide directly with an atomic nucleus in a detector. The challenge, and it is a monumental one, is that our world is an incredibly noisy place. We are constantly bombarded by a rain of high-energy particles from space called cosmic rays, as well as by natural radioactivity from the rocks and soil all around us. Any one of these normal particles could hit a nucleus in a detector and create a signal that looks exactly like a WIMP collision. To even have a chance of seeing the faint whisper of a WIMP, scientists must first find a place of almost perfect silence. And for this, they must go down, deep into the heart of the Earth. The journey to these experiments is a descent into profound stillness. Scientists have built their laboratories in the deepest parts of active and retired mines, or in great halls carved out of the rock beneath mountains. They go down a mile or more, allowing the immense weight of the overlying rock to act as a natural shield, absorbing the cosmic rays that bombard the surface and creating a sanctuary of cosmic quiet. Here, in the deep, stable dark, they build their detectors, which are some of the most sensitive and pristine instruments ever created. The core of a typical experiment is a target material, often a large tank filled with a liquefied noble gas like xenon or argon, or a collection of ultra-pure crystals of germanium or silicon, cooled to temperatures just fractions of a degree above absolute zero. The central idea is to watch these target nuclei with extreme vigilance, waiting for one of them to suddenly recoil, to get a tiny subatomic kick from an incoming WIMP. This recoil would be like a single billiard ball, previously at rest, being struck by an invisible cue ball. The energy of this tiny collision would then be converted into a faint, detectable signal. A tiny flash of light called scintillation, a small release of electric charge known as ionization, or a minute vibration. A sound wave traveling through the crystal lattice, called a phonon. These are the faint, telltale signatures that would announce the passage of a particle from the dark side of the universe. The engineering required to hunt for such an infinitesimal signal is breathtaking. Consider an experiment like the Large Underground Xenon, or LUX, and its successor, LZ, located nearly a mile beneath the Black Hills of South Dakota, or the X-Xenon NNT experiment, deep beneath the Gran Sasso Mountain in Italy. Their central vessels contain tons of liquid xenon, purified to a level that makes the cleanest air on Earth seem filthy by comparison, because even a single stray atom of a radioactive isotope could create a false signal. This inner sanctum is surrounded by an array of thousands of incredibly sensitive light detectors, ready to catch the faintest glimmer of a WIMP interaction. And this entire assembly is then nested within multiple layers of shielding, like a set of Russian dolls. A vessel of ultra-pure copper, a massive tank of purified water, and thick walls of lead, all designed to stop any last stray particle of normal matter from reaching the detector's heart. These experiments are the quietest places on Earth, monuments to the human capacity for patience, designed to listen for a single, fleeting event that might happen in their detector less than once a year, or perhaps only once a decade. It is a form of scientific meditation, a long and patient vigil in the dark. And so, for years, and now for decades, scientists have been listening in this profound, terrestrial silence. They have built ever larger, ever more sensitive detectors, pushing the frontiers of technology to listen for ever fainter whispers. And the result of all this patient listening has been, in its own way, just as profound as a discovery. They have heard nothing, a great and telling silence. No unambiguous, reproducible signal of a WIMP has ever been confirmed. This is not a failure. This null result is a tremendously important piece of scientific information. Each new generation of experiments has ruled out a wider range of possibilities for what the WIMP could be, telling us where the dark matter is not. The silence from these deep underground labs has told us that the simplest, most straightforward models of the WIMP, those that were once so compelling, are not correct. The universe is more subtle than we had hoped. This deep silence has closed many doors, but it has also forced open new ones, pushing theorists and experimentalists alike to contemplate more complex, more elusive candidates, and to develop new and even more ingenious strategies for the hunt. The sound of silence from the heart of the Earth is a message from the cosmos itself, a gentle redirection in our long and winding search for its hidden heart. While some listen for the whisper of an ancient WIMP in the deep and silent Earth, others attempt a completely different strategy, to forge a particle of darkness from the pure, brilliant light of energy itself. This second approach takes us from the quietest places on the planet to the most energetic, to the world of particle colliders. The grandest of these machines is the Large Hadron Collider, or LHC, operated by CERN near Geneva, Switzerland. It is one of the most magnificent scientific instruments ever built, a testament to what humanity can achieve when it works together to ask the biggest questions. To picture it, imagine a vast ring, a circular tunnel 27 kilometers in circumference, buried 100 meters beneath the French-Swiss countryside. Inside this tunnel are two parallel beam pipes, each thinner than a human hair, held in a near-perfect vacuum, colder than outer space. Down these pipes, two beams of protons are accelerated in opposite directions by thousands of powerful superconducting magnets, guided on their circular path until they are traveling at 99.999999% of the speed of light. At this incredible speed, each proton carries the kinetic energy of a flying mosquito, a colossal amount of energy to pack into a subatomic particle. Then, at 4 specific points along the ring, the two beams are steered into a head-on collision, concentrating this immense energy into a microscopic point in space. The purpose of this extraordinary undertaking is to harness one of the most profound principles in all of physics, captured in Einstein's iconic equation, E equals mc squared. This equation tells us that energy and mass are not separate things, but are two different aspects of the same fundamental cosmic currency. Energy can be converted into mass, and mass can be converted into energy. The LHC is a machine designed to perform this conversion in a spectacular way. The intense concentration of energy created in the proton-proton collisions momentarily recreates the conditions that existed in the universe less than a trillionth of a second after the Big Bang. In that fleeting, microscopic fireball, the raw energy of the collision can coalesce into new particles, often heavy and unstable particles that have not existed in our universe for over 13 billion years. The LHC, in this sense, is not just a microscope for seeing the smallest things, but also a telescope for looking back in time, a time machine that allows us to witness the kinds of particles that populated the primordial soup of creation. And the hope is that, among the known particles of the standard model that are forged in these collisions, we might also create particles of dark matter. We would not be detecting an ancient WIMP from the galactic halo, but rather creating a fresh, new one, right here on Earth. But this immediately raises a difficult question. How could you possibly detect a particle whose very nature is to be invisible and to pass through matter without a trace? The detectors at the LHC are colossal, multi-story digital cameras designed to record the trajectory, energy, and momentum of every single particle that flies out from a collision. They can see quarks, electrons, photons, and all the other known particles. But a newly created dark matter particle, a WIMP, would fly out from the collision point and pass through the entire detector without leaving a single signal, as if it were a ghost. The strategy, therefore, is to look not for the particle itself, but for its absence. It is a search for a conspicuous hole in the data, for a footprint of something that should be there but isn't. According to the fundamental law of conservation of momentum, the total momentum of all the particles flying out of a collision must balance out to zero, just as the recoiling pieces of an explosion in space would all fly away from a central point in a balanced way. The LHC detectors can measure the momentum of all the visible particles. If the measured momentum does not add up, if there is a significant imbalance, it would imply that one or more invisible particles must have been produced and carried away momentum in the opposite direction. This missing energy, or missing momentum, would be the telltale signature, the ghostly footprint of dark matter being forged in the light. This method, of trying to catch a glimpse of the invisible by meticulously accounting for everything visible, is an experimental tour de force. The LHC generates billions of collisions every second, and powerful computers sift through this torrent of data in real time, looking for the rare and interesting events that might signal new physics. After years of operation, this incredible machine successfully discovered the Higgs boson, the final missing piece of the standard model, a triumph that was celebrated around the world. But in its dedicated search for dark matter and other new particles, the LHC has, so far, shared the same fate as the underground experiments. It has found a profound and telling silence. The energy and momentum in its collisions have, with remarkable precision, always balanced. There have been no definitive signs of missing energy that would point to the creation of WIMPs. This, again, is not a failure. The data from the LHC has placed incredibly stringent constraints on the properties of dark matter, ruling out many of the simplest and most appealing WIMP theories. Together, the quiet listening in the deep earth and the energetic forging at the colliders have painted a new picture. They have shown us that if the WIMP does exist, it must be more elusive, perhaps heavier or more weakly interacting than we first imagined. The combined silence of our most ambitious experiments is pushing us to look further, to think deeper, and to wonder if the answer to the dark matter mystery lies in a completely different direction altogether. With the deep earth remaining quiet and the brilliant flashes of the colliders revealing no new shadows, the search for the WIMP turns to a third and final strategy, a method that looks neither for a particle arriving from space nor attempts to create one on Earth, but instead listens for the faint, final whisper of dark matter destroying itself in the cosmos. This approach, known as indirect detection, is born from a fascinating possibility within many theoretical models. It suggests that the WIMP particle might be its own antiparticle, much like the photon. If this is the case, then on the rare occasion that two WIMP particles meet in space, they could annihilate each other in a burst of pure energy. converting their entire mass into a shower of familiar, high-energy particles, according to the timeless law of E equals mc squared. This act of mutual destruction would be the final, fleeting signal of their existence. A tiny flash of light from the dark sector that might just be visible to our telescopes here on Earth. The strategy of indirect detection is therefore a form of cosmic archaeology, searching for the faint, energetic ashes of a dark matter fire. We are not looking for the dark matter itself, but for the standard, visible particles that are produced in its demise. The key to this search is knowing what to look for and where to look. The annihilation of two massive WIMPs would produce a cascade of particles that we are well equipped to detect. Chief among them would be gamma rays, the most energetic form of light, with energies far exceeding those of visible light or X-rays. A WIMP annihilation event would produce gamma rays with a very specific, characteristic energy, directly related to the mass of the WIMP itself, providing a potential smoking gun signature. The annihilation could also produce other exotic particles, such as a surplus of antimatter, like positrons, the antimatter equivalent of electrons or antiprotons. It could also create a flux of high-energy neutrinos, the famously elusive ghost particles of the Standard Model, which travel across the universe in straight lines from their source. The challenge is that the universe is already filled with high-energy phenomena. Exploding stars, rapidly spinning neutron stars called pulsars, and the supermassive black holes at the centers of galaxies are all prodigious sources of gamma rays, antimatter, and neutrinos. The task of the indirect detection astronomer is therefore a delicate one, to find a faint, anomalous signal, a mysterious excess of these particles that cannot be explained by any known astrophysical source, a whisper of annihilation hidden within a cosmic storm of natural background noise. Success in this endeavor hinges entirely on pointing our telescopes at the right places. Since the rate of annihilation depends on the square of the dark matter density, you need two WIMPs to meet. After all, the signal should be overwhelmingly strongest in regions where dark matter is most densely packed. The most obvious target is the very center of our own Milky Way galaxy. The dark matter halo is thought to rise to a sharp peak, or cusp, in the galactic core, making it the brightest potential source of annihilation signals on the sky. Another prime location is the collection of small, faint dwarf spheroidal galaxies that orbit our Milky Way. These tiny satellite galaxies are fascinating objects. They are the most dark matter-dominated structures we know of, with up to 1,000 times more dark matter than visible matter. This makes them incredibly clean laboratories for this search, as they have very few stars and very little gas, and thus almost no conventional astrophysical sources to create a confusing background signal. Finally, astronomers also look to the great galaxy clusters, the most massive reservoirs of dark matter in the entire universe, hoping to see a faint, diffuse glow of gamma rays from the annihilation happening within their colossal halos. To conduct this cosmic hunt, scientists have deployed an array of extraordinary observatories, each designed to capture a different kind of particle messenger from the heavens. Orbiting high above the Earth's atmosphere is the Fermi Large Area Telescope, a powerful gamma-ray space observatory that has been scanning the entire sky for over a decade, creating the most detailed map ever made of the high-energy universe. Attached to the International Space Station is the Alpha Magnetic Spectrometer, or AMS, a state-of-the-art particle detector that is meticulously measuring the flux of cosmic rays and antimatter arriving at Earth, searching for any telltale excess. And buried a mile deep in the pristine ice of the South Pole is the Ice Cube Neutrino Observatory, a truly colossal detector that uses a cubic kilometer of ice as its detection medium, watching for the faint flashes of light produced when a high-energy neutrino from space interacts with an ice molecule. These incredible experiments, and others like them, have indeed found intriguing puzzles. The Fermi telescope has detected a mysterious excess of gamma rays coming from the galactic center, and the AMS has seen a curious surplus of positrons. But for each of these hints, there are plausible, if not definitive, alternative explanations from conventional astrophysics, like swarms of undiscovered pulsars. And so, just like its counterparts in the deep Earth and in the great colliders, the search for dark matter's annihilation has been met with a tantalizing, but ultimately inconclusive, silence. The ghost remains a ghost, its final whisper indistinguishable from the natural murmurs of the cosmos. This profound, threefold silence, echoing from the deepest minds, the most powerful colliders, and the darkest corners of the cosmos, has gently steered the river of scientific thought into new and unexpected channels. For decades, the WIMP had been the dominant paradigm, a compelling and beautiful idea that seemed to fit the evidence so perfectly. But the persistent lack of discovery has led to a quiet but important revolution in our thinking. If dark matter is not the massive, bullet-like WIMP, perhaps it is something far stranger, something more ethereal, less like a particle, and more like a pervasive, cosmic wave. This shift in perspective has brought a new, and in many ways much older, candidate to the forefront of the search. A hypothetical particle known as the axion. And the story of the axion is a wonderful example of the interconnectedness of scientific inquiry, for it was not invented to solve the dark matter problem at all, but was born from a completely different and far more subtle puzzle within the heart of the Standard Model. In the late 1970s, particle physicists were grappling with a question known as the strong CP problem. To put it gently, the theory of the strong nuclear force, the force that binds quarks together inside protons and neutrons, allows for a certain kind of asymmetry in its interactions, a violation of what is known as charge parity, or CP symmetry. The problem is that when we perform experiments, we find that the strong force is, in fact, perfectly symmetric in this regard, to an astonishingly high degree of precision. There seemed to be no fundamental reason why this should be so. It was as if we had found a pencil perfectly balanced on its tip, a state that is possible, but exquisitely unnatural. To solve this puzzle, the physicists Roberto Peccei and Helen Quinn proposed a new mechanism that would naturally and dynamically restore the symmetry, forcing the pencil to lie flat on its side. And a few years later, others realized that this new mechanism implied the existence of a new particle, a particle that was later christened the axion, after a brand of detergent, because it cleaned up this messy problem in the theory. The axion, then, was proposed as a key for a completely different lock, a piece of elegant theoretical machinery to solve an internal problem of the Standard Model. It was only later that physicists began to realize the profound cosmological implications of this idea. If the axion exists, its properties would make it an ideal candidate for dark matter. The theory predicts that it would be an incredibly light particle, perhaps 1 billion or even 1 trillion times lighter than a single electron, a true featherweight ghost of the subatomic world, and its interactions with all other particles would be exceptionally, almost unimaginably, feeble, far weaker even than the WIMP. This would make it perfectly stable, completely invisible, and would allow it to pass through matter with even greater ease than its heavier counterpart. Crucially, axions would have been produced in the early universe, through a process entirely different from the thermal freeze-out of WIMPs. They would have been created in colossal numbers through a process known as vacuum realignment, emerging not from the fire of a thermal bath, but from the settling of a new, universe-spanning energy field. The result is that even though each individual axion carries an infinitesimal amount of mass, their sheer, overwhelming abundance could easily provide the 5/6 of the universe's matter density that we attribute to dark matter. This different origin story leads to a profound difference in how we should imagine axion dark matter. WIMPs are best pictured as a gas of individual, bullet-like particles flying through space. But because axions are so fantastically light, and were all created in a coherent way, they are better described not as a collection of particles, but as a single, continuous, classical wave that fills all of space. Imagine the dark matter halo of our galaxy not as a swarm of invisible bees, but as a vast, silent, and invisible ocean. The particles we call axions are merely the smallest possible quantum ripples on this ocean, but the ocean itself behaves as a single, unified entity. Furthermore, this cosmic field is not static. It is oscillating, vibrating at a very specific frequency that is directly related to the axion's mass. The entire universe, in this picture, is filled with the silent, rhythmic hum of this invisible axion field. Dark matter is not a storm. It is a song, a single, pure note of unimaginable length and subtlety, playing constantly in the background of reality. If dark matter is a wave, then our methods for detecting it must change. You do not use a microphone to find a radio station. You use a radio. This is the guiding principle behind axion detection experiments, which are often called haloscopes, because they are designed to look for the axion in our galactic halo. One of the leading experiments of this kind is the Axion Dark Matter E experiment, or a DMX. The ingenious idea is to harness a subtle prediction of axion theory. In the presence of a very strong magnetic field, an axion from the cosmic field can, on a very rare occasion, convert into a photon of light. This photon would have an energy, and thus a frequency, that is precisely equal to the oscillation frequency of the axion field. So, the ADMX experiment consists of a hollow, resonant cavity placed inside the powerful magnetic field of a superconducting magnet and cooled to near absolute zero to minimize background noise. This cavity is then connected to the world's most sensitive microwave amplifiers. The entire apparatus is, in essence, a radio, designed to listen for the incredibly faint microwave photon that would be the signature of an axion conversion. Scientists must then slowly and patiently tune the resonant frequency of this radio, sweeping through the possible frequencies, listening for the single, persistent note of the axion against the static of the cosmos. It is a search of immense delicacy, a quiet and meditative act of tuning into the silent music of the invisible world. This ethereal image of a universe humming with a silent, oscillating field is one beautiful possibility. But there is another path into the darkness, one that begins not with a completely new theoretical invention, but with a ghost that we already know, a shy and elusive particle that is already part of our standard model. The neutrino. For as long as we have known of them, neutrinos have been the most ghostly of all the known particles. They were first proposed in the 1930s to solve a crisis in physics, an apparent violation of the law of conservation of energy in certain radioactive decays. It seemed that some energy was mysteriously vanishing. The physicist, Wolfgang Pauli, made a daring proposal. Perhaps the energy was being carried away by a new, invisible particle, one with no electric charge and a very tiny, perhaps even zero, mass. He called it the little neutral one, or neutrino. It was a particle born as a ghost, invoked to balance a cosmic ledger, and for decades it remained a ghost, so difficult to detect that it was thought to be impossible. But we did eventually detect them, and we have learned that they are all around us. Trillions of neutrinos, produced in the fiery heart of our sun, are streaming through your body every single second of every day. A constant, silent, and utterly harmless rain of particles from space. For many years, the standard model of particle physics held that neutrinos, which come in three different types or flavors, the electron neutrino, the muon neutrino, and the tau neutrino, were perfectly massless. But in the late 1990s, a series of stunning experiments, most notably at the Super Kamiokande Observatory in Japan, made a discovery that shook the foundations of particle physics. They found that neutrinos can change their identity as they travel, a process called neutrino oscillation, in which an electron neutrino might spontaneously transform into a muon neutrino and back again. This shape-shifting is only possible if neutrinos have mass. The discovery of neutrino mass, as tiny as it may be, was the first major, undeniable crack in the otherwise perfect edifice of the standard model. It was a clear and powerful signal that our map of the subatomic world was incomplete, that there was new physics waiting to be discovered. The fact that neutrinos have mass at all is a deep mystery, one that the standard model cannot explain, and it is in the attempts to solve this mystery that a new dark matter candidate emerges, a particle that is tantalizingly close to what we already know. One of the most elegant ideas proposed to explain the origin of neutrino mass is a theoretical mechanism that postulates the existence of a new kind of neutrino, a fourth flavor, that is very different from the other three. The three known neutrinos are what we call left-handed in a quantum mechanical sense, and they all participate in the weak nuclear force. The theory suggests that there might also exist a right-handed counterpart, which would be completely impervious to the weak force. This hypothetical particle is known as a sterile neutrino. The name is beautifully descriptive. It would be sterile in the sense that it is completely cut off from almost all the familiar interactions of our world. It would not feel the strong force, the electromagnetic force, or even the weak force. It would be a true hermit of the particle world, a silent and solitary entity whose only connection to our universe, its only way of making its presence known, would be through the gentle and universal pull of gravity and through a subtle quantum mechanical mixing with the other three neutrinos that gives them their tiny mass. If it exists, the sterile neutrino represents a kind of shadow particle, a hidden sibling to the neutrinos we know, living in a state of almost perfect isolation. It was not long before cosmologists realized that this sterile neutrino, invented to solve a problem in particle physics, also had the potential to solve the dark matter mystery. If these particles were produced in the right quantities in the hot, dense conditions of the early universe, their combined mass today could easily account for all of the missing matter. They are stable, they are dark, and they interact so feebly that they fit the collisionless criteria we see in the bullet cluster. However, a dark matter universe made of sterile neutrinos would look subtly different from one made of heavy WIMPs or ethereal axions. Because sterile neutrinos are expected to be much lighter than WIMPs, they would have been moving much faster in the early universe when the first structures began to form. This makes them a candidate for what is known as warm dark matter. This extra speed has a crucial consequence. It would tend to wash out, or erase, the very smallest of the primordial density fluctuations. A stream of fast-moving particles cannot easily clump together to form very small objects. A warm dark matter universe, therefore, would have a harder time forming the smallest galaxies. We would expect to find fewer tiny dwarf satellite galaxies orbiting the Milky Way compared to the predictions of the standard cold dark matter model. And so, a new line of inquiry has opened up, with astronomers carefully counting the population of these faint satellite galaxies, trying to see if our local universe is missing some of its smallest members, a possible clue that the dark matter we are searching for is not cold, but warm, and that its identity is this profoundly silent and sterile particle, a ghost that has been hiding in the shadow of a ghost we already knew. In our search for the substance of the invisible world, we have hunted for massive WIMPs, listened for ethereal axions, and considered the lonely silence of sterile neutrinos. All of these quests share a common, foundational assumption, that our understanding of gravity is correct, and that there must therefore be a vast amount of missing substance to explain our observations. But what if this assumption, as solid as it seems, is flawed? What if there is no missing substance, no new particle to be found? What if the ghost we have been chasing is not a ghost at all, but rather a misunderstanding of the very laws of gravity that led us to believe in it in the first place? This is the most radical and, in many ways, the most intellectually challenging alternative to dark matter. A line of thought that asks us not to add new ingredients to the cosmic recipe, but to rewrite the recipe book itself. It is an idea that suggests that the universe's invisible grip is not the pull of unseen matter, but the signature of a deeper and more complex law of gravity. This alternative paradigm is known as MOND, which stands for Modified Newtonian Dynamics. It was proposed in the early 1980s by the Israeli physicist Mordechai Milgrom. He began with the very observation that started our modern search for dark matter, the puzzlingly flat rotation curves of spiral galaxies. Instead of hypothesizing an enormous halo of invisible particles to explain why the outer stars move so fast, Milgrom proposed a startlingly simple, yet profound, idea. He suggested that Newton's famous inverse square law of gravity, the law that has perfectly described everything from falling apples to the orbits of planets for centuries, is not the whole story. He proposed that this law is an excellent approximation in regions of high acceleration, like our solar system, but that it changes its mathematical form in the extremely low acceleration environments that characterize the outskirts of a galaxy. In these regions, where the gravitational pull is thousands of millions of times weaker than what we feel on Earth, Milgrom suggested that gravity becomes slightly stronger than Newton's law would predict, declining more slowly with distance. It is not that there is extra matter pulling on the outer stars, it is that gravity itself pulls more tenaciously at these great distances and low accelerations. The most striking feature of MOND is its remarkable success in explaining the dynamics of galaxies. Without any need for dark matter, the theory's modified law of gravity predicts that the rotation curves of spiral galaxies should become flat at large distances, exactly as Vera Rubin observed. What is more, it provides a natural explanation for a tight empirical relationship, known as the Tully-Fisher relation, which connects a galaxy's total luminosity, the amount of light from its visible, baryonic matter, to its rotation speed. In the dark matter paradigm, this relationship is something of a mystery, but in MOND, it is a direct and natural consequence of the theory. For many years, MOND has been a persistent and sometimes vexing challenger to the standard cosmological model, because on the scale of individual galaxies, it often provides a more elegant and more accurate description of the observations with fewer adjustable parameters than the more complex dark matter models. It represents a completely different way of seeing the universe, a universe where what you see is what you get, and where the laws of nature themselves can be more subtle and nuanced than we ever imagined. However, for all of its elegance on the galactic scale, MOND has faced significant and persistent challenges when confronted with observations on larger, cosmological scales. While the original formulation of the theory could explain the motion of galaxies, it struggled mightily to account for the dynamics within great galaxy clusters. Even with modified gravity, a huge amount of missing mass was still required to hold these enormous structures together. More critically, MOND, in its simplest form, offers no natural explanation for the stunning observations of the Bullet cluster. The clear separation of the center of mass, mapped by gravitational lensing, from the center of the visible, baryonic matter, is incredibly difficult to explain if there is no collisionless, invisible substance that can pass through the collision like a ghost. Any modified theory of gravity must somehow explain why the gravitational field is centered where there is very little visible matter. And perhaps most damningly, MOND struggles to reproduce the incredibly precise and detailed pattern of peaks and troughs that we observe in the cosmic microwave background, a pattern that is perfectly explained by the standard model of cold dark matter and the acoustic oscillations of the early universe. And so, we are left with a fascinating and productive tension in modern cosmology. We have the standard model of dark matter, which works beautifully on the largest cosmological scales but sometimes struggles with the finer details of individual galaxies. And we have MOND, which works beautifully on the scale of individual galaxies but struggles on the largest scales. This ongoing debate is not a sign of a crisis in science, but a sign of its profound health. The existence of a credible alternative like MOND forces dark matter proponents to refine their models and find more definitive proof, while the successes of the standard model force proponents of modified gravity to develop their theories to encompass the whole of cosmic history. The ultimate answer may not be a simple victory for one side over the other. It may be that the truth is something richer, a new theory that incorporates elements of both, perhaps a new particle that also interacts in a way that modifies the behavior of gravity. The altered song of MOND serves as a profound and vital reminder that in our quest to understand the universe, even our most sacred and foundational laws are not beyond question, and that the deepest mysteries may require us to change not just what we see, but the very way we look. This rich and fascinating tension between a universe filled with an unseen substance and a universe governed by an unseen law has inspired a new generation of ideas, theories that suggest the truth may not be a simple choice between one or the other. Perhaps the invisible world is not a single, lonely particle, but an entire hidden ecosystem, a parallel world as complex and intricate as our own. For many years, our search was guided by the principle of simplicity, the hope that a single, elegant particle like the WIMP would solve the entire puzzle. But as our experiments have come back silent, a new and more complex picture has begun to emerge, a picture that asks a profound question. Why should the dark side of the universe be any simpler than the bright side? Our own visible world is not made of just one particle. It is a rich and vibrant menagerie of quarks, leptons, and the force-carrying bosons that weave them together into the beautiful tapestry of atoms, molecules, stars, and life. Perhaps we have been too timid in our imagination. Perhaps the invisible world is just as rich, just as complex, a universe hiding in plain sight. This leads us to the breathtaking concept of a dark sector. The idea is that dark matter is not a single particle, but rather a whole family of different particles, a shadow world with its own unique constituents. Just as our visible sector has the electron, the proton, and the photon, the dark sector might have its own dark electron or dark proton particles with their own unique properties, all of which are invisible to us. This is not just idle speculation. It is an attempt to imagine a more complete and symmetric universe. It suggests that the standard model, our map of the visible world, might have a corresponding dark standard model, a set of particles and rules that govern the 85% of matter that we cannot see. The two sectors, the light and the dark, would exist concurrently, occupying the same space, permeating our entire universe, yet remaining almost entirely oblivious to one another's existence, like two different radio stations being broadcast on completely different frequencies. Their only significant point of contact, the only bridge between these two worlds, would be the universal and democratic force of gravity, which feels all mass and energy, regardless of its origin. If a dark sector with multiple particles exists, it opens up an even more fascinating possibility: the existence of dark forces. After all, the particles of our visible world are governed by a suite of forces: electromagnetism, the strong force, the weak force. Why should the dark sector be any different? It is possible that the particles of the dark sector interact with one another through their own unique, undiscovered forces. Physicists have theorized about the existence of a dark photon, a particle that would be the carrier of a kind of dark electromagnetism. While we would be completely blind to this dark light, the particles of the dark sector would feel it. They could attract and repel one another, form dark atoms, and perhaps even create a kind of dark chemistry, giving rise to complex, invisible structures that we have not even begun to imagine. This idea of a self-interacting dark matter, or SIDM, is not just a fantasy. It has the potential to solve some of the subtle, lingering puzzles in our understanding of the cosmos. For example, when we look at the very centers of some smaller galaxies, we find that the dark matter cores are often less dense and more puffy than the simplest cold dark matter simulations would predict. If dark matter particles can interact with each other, if they can gently collide and bounce off one another via a dark force, it would naturally explain this puffiness, as the interactions would tend to spread the particles out, lowering the central density. This grand, emerging vision transforms our perception of dark matter entirely. It suggests that the invisible universe is not a simple, inert, and silent gravitational scaffolding. It could be a place of immense dynamism and complexity, a hidden valley of physics operating by rules we do not yet know, unfolding its own cosmic story in parallel to ours. The silence from our experiments, in this light, might not be a sign that we are looking for the wrong thing, but a sign that the reality is far more subtle and intricate than our first simple models. It may be that dark matter is not a single entity to be discovered, but a new physics to be unfurled, a new continent of reality whose coastline we have only just glimpsed. The 85% of the universe that is dark is not necessarily empty or boring. It is simply unknown. And to contemplate this is to stand in a state of profound and humbling awe. It is to look up at the night sky and to understand that the darkness between the stars is not an absence, but a presence, a plenum, a hidden cosmos whose complexity and richness might rival, or even exceed, our own. The journey into the invisible world has led us not to a simple answer, but to a deeper and more wondrous appreciation for the sheer depth of the mystery itself. This vast, hidden cosmos, with its potential for unseen forces and unknown particles, may feel distant and abstract. And yet, its presence is woven into the very fabric of our own story. For without this silent, invisible scaffolding, our galaxy, our sun, and our own small, fragile world would never have had the chance to exist. As our journey through the science of this invisible world begins to draw to a close, we turn now to its most intimate and profound implication, the unexpected and unbreakable link between the largest scales of the cosmos and the delicate, improbable miracle of our own consciousness. We are beginning to understand that dark matter is not merely an astronomical curiosity, but is, in a very real sense, the cradle of our existence, the silent, nurturing presence that made our home possible. To truly feel this connection, let us perform a simple thought experiment. Let us imagine a universe exactly like our own in every respect but one. It contains no dark matter. In this imaginary cosmos, the Big Bang still happens. The primordial elements of hydrogen and helium are still forged in the first 3 minutes, and the cosmic microwave background is still released as the universe becomes transparent. But without the immense gravitational influence of dark matter, the story of what happens next changes dramatically. The initial density fluctuations, the tiny seeds of structure, are still there, but now only the feeble gravity of the normal, baryonic matter is available to act upon them. The outward, expansive force of the universe would have almost completely overwhelmed this weak gravity. The process of structure formation would have been incredibly slow and inefficient. Galaxies, if they formed at all, would have taken many more billions of years to coalesce, and they would be far smaller, more anemic, and more diffuse than the grand spirals we see in our own universe. The majestic Milky Way, our galactic home, would likely not exist. In its place might be a small, disorganized clump of stars, or perhaps nothing at all. The universe would be a far more empty and far less structured place, a cosmos of scattered gas clouds, and very few, if any, great stellar cities. But let us suppose that a galaxy somewhat like our own did eventually manage to form. Even then, its internal dynamics would be profoundly different without the calming, stabilizing presence of a dark matter halo. For life to evolve on a planet like Earth, it needs an immense amount of time, billions of years of relative stability. Our solar system completes an orbit around the center of the Milky Way roughly every 240 million years, and it has done so in a remarkably stable, nearly circular path for its entire 4.5 billion year history. This long, serene journey has been essential for our existence, keeping us safely within the galaxy's habitable zone, a celestial sweet spot where there are enough heavy elements to build rocky planets, but not so much violent radiation or gravitational disruption that life would be constantly sterilized. This stability, this predictable and gentle orbit of our Sun, is a direct consequence of the galaxy's dominant, spherical dark matter halo. The immense, smoothly distributed mass of the halo acts as a great gravitational anchor, evening out the lumpy, irregular pull of the visible spiral arms, and ensuring that the stars within it travel on well-behaved, orderly paths. Without the halo, our Sun's orbit would be far more chaotic, potentially plunging us into the dangerous inner regions of the galaxy or casting us out into the barren outer regions, a journey that our delicate biosphere would not survive. And so, we are led to a conclusion that is as humbling as it is awe-inspiring. Our existence is contingent upon the existence of a substance we cannot see, cannot touch, and cannot yet comprehend. We are here because the dark matter was here first. It was the dark matter that gathered the primordial gas, providing the gravitational wells deep enough to form the first galaxies quickly and efficiently. It was the dark matter that shaped our Milky Way into a grand, stable spiral, a safe harbor for stars and planets. And it is the dark matter that continues to hold our solar system in its gentle, life-sustaining orbit. This invisible substance is not some alien or peripheral feature of the cosmos. It is the very foundation upon which our cosmic home is built. To reflect on this is to feel a new and profound sense of connection to the universe. It is to look at the dark night sky and see not an emptiness, but a nurturing presence. The darkness is not a void, it is a cradle. The silence is not an absence, but the quiet strength of the foundation that supports us. We are, in the most literal sense, children of the darkness. Our existence made possible by a ghost we are only just beginning to know. And in this knowledge, there is a deep and abiding peace, a sense of belonging to a universe far stranger and far more benevolent than we ever dared to imagine. This profound and unexpected connection, linking our physical existence to the universe's invisible architecture, invites us to turn our gaze inward, to explore a parallel mystery that resides not in the cosmos, but within the quiet, hidden depths of our own consciousness. For just as the universe of stars and galaxies is but a luminous froth on the surface of a vast dark ocean, the part of our own mind that we experience, our conscious awareness, is but the visible tip of a far greater and largely invisible psychological continent. The journey to understand dark matter, with its reliance on inference, its search for faint signals, and its humbling revelations, offers us a beautiful and powerful metaphor for the equally profound journey of self-knowledge, the quest to understand the unseen forces that shape the landscape of our inner world. For over a century, psychologists and philosophers have used the metaphor of an iceberg to describe the human mind. The small portion visible above the water is our conscious awareness. It is the seat of our focused attention, our logical reasoning, our immediate perceptions, and the voice of our inner monologue. This is the part of ourselves that we identify with, the part that we believe is in control, the luminous eye that narrates our experience of the world. But just as with the cosmos, this visible part is by far the smallest. Beneath the surface of the water lies the vast, immense, and powerful mass of the unconscious. This is the great repository of our being, a hidden world containing all the memories we have forgotten, the instincts and archetypes inherited from our evolutionary past, the deep-seated beliefs and emotions that were formed in our earliest years, and the powerful drives and desires that we may not even know we possess. This unconscious realm is the dark matter of our minds, and its influence, though unseen, is every bit as powerful and pervasive as the cosmic substance that holds the galaxies together. We can feel the gravitational pull of this inner dark matter in the subtle, and sometimes not so subtle, ways our own minds work. We pride ourselves on being rational creatures, on making decisions based on logic and evidence. But modern psychology has revealed that our reasoning is constantly being shaped and guided by a vast web of unseen cognitive biases and mental shortcuts. These are the ingrained patterns of thought, the well-trodden neural pathways that influence our judgments without our conscious permission. They are the invisible gravitational forces that gently, but persistently, pull our train of thought off its straight, logical track. When we fall prey to confirmation bias, seeking out information that supports what we already believe, we are feeling the gravitational pull of a deep, unconscious need for certainty. When we make a snap judgment about a person based on a first impression, we are following a swift, ancient, and unconscious heuristic that evolved for survival in a simpler world. These forces are not necessarily malicious, they are part of our mental architecture, but like the dark matter in a galaxy, they are the unseen mass that dictates the true shape of our mental orbits, revealing that our conscious reasoning is often less a commander and more a passenger, traveling along paths that were laid down long before it came into being. And what of those mysterious flashes of insight, those sudden gut feelings or moments of profound intuition that seem to arrive from nowhere, fully formed and imbued with a deep sense of certainty? Perhaps we can think of this as a kind of mental gravitational lensing. An intuition is a piece of knowledge whose logical path to our conscious mind is obscured. It is a conclusion that has been reached not by a linear, step-by-step process, but by the parallel, superconscious processing of the vast networks of our unconscious mind, which can sift through a lifetime of experience in an instant. This immense, hidden structure can bend and focus information in ways our conscious mind cannot, presenting us with a distorted, magnified, but often deeply true image of reality. And the work of getting to know ourselves, the patient and sometimes difficult practices of introspection, of meditation, of journaling, or of therapy, can be seen as our own form of direct detection. These are our attempts to build a quiet space, a laboratory deep within ourselves, shielded from the constant noise and cosmic rays of daily life. In this inner silence, we learn to listen, to watch for the faint signals, the emotional recoils, the symbolic images of our dreams that betray the presence and the nature of our own hidden matter. The journey into the cosmos and the journey into the self are one and the same, a patient, humbling, and ultimately deeply rewarding attempt to map the contours of a beautiful and ever-present darkness. And so we find ourselves suspended between two vast and silent oceans of the unseen, one without and one within. The journey to know them is not just a scientific one, it is a profoundly human and creative act, an art of seeing the invisible. As we have travelled through the story of dark matter, from the first puzzling motions of the galaxies to the deepest and most sensitive experiments on Earth, One common thread has run through every chapter. We have never once seen the thing itself. We have only ever seen its shadow, its echo, its footprint on the world of light. This is the very nature of fundamental inquiry, a truth that extends far beyond the search for dark matter. It is the quiet and often overlooked philosophical heart of the entire scientific enterprise. Science, at its deepest level, is the art of inferring the unseen from the seen. Think of the great discoveries that form the bedrock of our modern world. No human being has ever truly seen an electron. We have seen the glowing trail it leaves in a cloud chamber, the way it makes a phosphor screen light up, or the reading it produces on a sensitive instrument. We deduce its existence and its properties from these effects, these interactions with the world we can see. No one has ever directly observed the quantum field that permeates all of space. We see its nature only when we excite it with enough energy to produce a particle, a fleeting ripple that betrays the presence of the underlying ocean. In the same way, we know of black holes not by seeing the objects themselves, but by watching the frantic dance of stars caught in their gravitational embrace, or by seeing the brilliant flare of matter as it falls across the event horizon. The entire history of physics is a history of learning to read the clues, of becoming masterful detectives who can reconstruct the nature of the culprit from the faintest of fingerprints left at the scene. The search for dark matter is the current, grandest chapter in this noble and creative tradition, a collective human effort to paint a portrait of a subject that refuses to sit still and will not show its face. This process is not merely one of cold, mechanical deduction. It is an act of profound and disciplined imagination, an endeavor that shares a deep kinship with the arts. When a cosmologist designs a great supercomputer simulation, carefully inputting the laws of physics and the initial conditions of the universe, and then watches as a cosmic web of breathtaking complexity grows and unfolds in digital form, is it so different from a composer arranging the notes of a symphony, letting them blossom according to the rules of harmony and rhythm into a magnificent whole? When an experimentalist imagines a new way to listen for the whisper of an axion, designing a resonant cavity and a magnetic field to convert a particle of darkness into a photon of light, is it not an act of creative inspiration? Akin to a poet finding the perfect metaphor to capture a feeling that cannot be named directly. The scientists who pursue this great mystery are not just technicians, they are artists of reality, using the materials of mathematics, metal, and silicon to build new senses for humanity, allowing us to perceive the contours of a world that lies far beyond the natural limits of our eyes and ears. And in this creative act, there is a deep and often misunderstood beauty in the role of failure, in the meaning of the persistent silence that has met our searches so far. We are often conditioned to see a null result as a dead end, a disappointment. But in the art of discovering the universe, the null result is one of our most powerful and important tools. We can see it through the eyes of a sculptor who stands before a great, shapeless block of marble. The final, beautiful form of the statue is already hidden within the stone. The sculptor's art is not just to add, but to subtract. With every tap of the chisel, a piece of stone that is not the statue is removed. The silence from our WIMP detectors is that chisel. Every null result carves away a piece of the marble of possibility, removing a universe that is not ours, and in so doing, bringing us closer to the true form of the reality that lies within. The silence is not an empty void. It is a sculpting tool, and the shape it is revealing is more subtle, more elegant, and more mysterious than our first simple sketches. It is this persistent mystery that keeps the universe alive for us, that fuels our curiosity and our wonder. A universe with all its questions answered would be a static and finished thing. The enduring puzzle of dark matter is a gift, a grand and beautiful question that invites us to keep looking, to keep imagining, and to keep listening to the profound and beautiful silence of the cosmos. And as we learn to live with this beautiful, sculpted silence, to find a sense of peace in the persistence of the mystery, we can allow our imagination to drift into one final, all-encompassing image, a metaphor that dissolves the boundaries between ourselves and the cosmos, and immerses us in the very substance of the invisible world. Let go now of the individual particles, the theories, the experiments, and allow yourself to drift into a new and comforting reality. Imagine that all of space, the vast perceived emptiness between the stars and the galaxies, is not a vacuum. Imagine that it is, instead, filled with a deep, calm, and perfectly transparent ocean. This ocean has no surface and no floor. It is infinite, extending in all directions, and it has existed since the dawn of time. This silent, invisible ocean is the dark matter, and everything that we have ever known, everything that shines and glitters in the cosmos, is but a fleeting and delicate luminescence within its depths. Our Milky Way galaxy is a single, beautiful, bioluminescent spiral, a living lantern of light adrift in this immense and unseen sea. And we, on our small, protected Earth, are like creatures of the reef, living our lives in a small, warm, and well-lit corner, largely unaware of the immeasurable, silent depths that surround us and give our home its form and its stability. Feel this cosmic ocean all around you. It is not cold or menacing. It is simply present. The constant, gentle stream of dark matter particles passing through you is reimagined now as the water of this ocean, flowing through you, becoming part of you. There is no distinction between your body and the medium in which it floats. You are of the ocean, and the ocean is in you. It is the substance that connects all things, the unifying medium in which all the bright islands of matter are suspended. When you look out across the cosmos, you are not looking through an emptiness, but through the endless body of this invisible sea. And the great cosmic web, the network of filaments that stretches across the universe, is revealed to be the slow, majestic, and powerful currents of this ocean. These are the deep, abiding rivers of substance that flow through the abyss, and their gentle, persistent motion has, over billions of years, shepherded the shining shoals of galaxies into the patterns we see today, gathering them into great clusters at the confluences, and leaving behind the vast, still, and peaceful basins that we call the voids. In this immersive world, the force of gravity is transformed. It is no longer a mysterious pull from a distant, unseen object, but is instead felt as the gentle, constant, and life-sustaining pressure of the deep. The immense weight of the dark matter halo that surrounds our galaxy is not a cage, but an embrace. It is the steady, uniform pressure of the ocean that holds our fragile, luminous world together, protecting it from the turbulent tides of the cosmos and allowing life to flourish in its calm, protected depths. It is a pressure that is so perfectly balanced, so serene, that we do not feel it as a force, but simply experience it as the stable and predictable nature of our reality. It is the quiet stillness of the abyss, a silence that is not empty, but is full of a powerful, structuring, and benevolent presence. There is nothing to fear in this darkness. The depths are not a threat, they are our home. They are the true substance of the universe, and the light is but a beautiful, fleeting, and precious exception. So let your awareness dissolve into this peaceful, cosmic sea. Let go of the feeling of being a separate observer, and allow yourself to become one with the medium. You are a part of this great, invisible, and silent entity, drifting peacefully in its timeless currents. There is no up or down, no beginning or end, only the gentle, all-encompassing presence of this ocean of being. Feel its quiet strength supporting you, its immense stillness bringing a profound calm to your own mind and body. This is the ultimate truth of our connection to the universe. We are not small, isolated beings looking out at a vast emptiness. We are integral parts of a vast, and mostly invisible, whole, sustained and cradled by a substance that we are only just beginning to comprehend. And in this understanding, there is a deep and profound sense of peace, a feeling of coming home to the true nature of reality, a silent, dark, and deeply comforting embrace. And so we float, weightless and serene, in this deep and silent ocean of being. And as we do, our gaze is gently drawn back to where our journey began, the simple, profound beauty of the night sky. But we see it now not with the same eyes. The darkness we once saw as a mere backdrop for the stars, a canvas of empty space, has been transformed. It is no longer an absence. It is a presence. Our long journey into the invisible world has taught us that the true story of the cosmos is written not in the light, but in the night. The darkness is not the exception, it is the rule, the fundamental fabric of which our universe is woven. And to know this, to truly feel it, is to find a new and lasting comfort in the quiet solitude of the night. When you look up at the stars now, you can remember that the pinpricks of light, as beautiful as they are, represent less than 5% of the cosmic story. All the rest, the vast majority of the matter that makes up our universe, is this gentle, invisible substance. The universe is not a collection of lonely, flickering candles in an infinite, empty void. It is a full house, a space teeming with a quiet and dignified presence, a substance that gives the cosmos its shape, its stability, and its grandeur. The darkness is not empty, it is full, and this thought can be a comforting blanket as you prepare for sleep. You are not alone in an empty universe, but are an intimate part of a full and mysterious one, held safely within its immense and invisible structure. And we can find further peace in the gentle nature of this connection. This substance that outweighs us all, that governs the fate of galaxies, is at the same time utterly and completely harmless to us. It is a presence so subtle, so shy, that it passes through our world and our bodies as if we were ghosts. Its only touch is the most reliable and steadfast force we have ever known. The gentle, persistent pull of gravity that holds us to the Earth and holds the Earth in its graceful orbit through the cosmos. It is the ultimate silent partner, the unseen guardian, the strong and quiet foundation upon which our entire luminous world is built. It asks nothing of us, and yet it gives us everything, the very stability and structure needed for life itself to emerge and to wonder about the nature of its own cradle. And so, we end our journey where we must, with the beautiful, enduring, and unanswered question. We do not know for certain what this substance is. The identity of dark matter remains one of the greatest and most profound mysteries in all of science. It may be an undiscovered particle, a ripple in a cosmic field, or something stranger than we have yet been able to imagine. And in this not knowing, there is a final and profound lesson. The universe does not owe us all of its answers. The joy is in the search, the wonder is in the questioning, and the beauty is in the persistence of the mystery. To be alive and conscious is to have the privilege of living with this grand and beautiful question, to look out into the darkness and to feel not a fear of the unknown, but a deep and abiding sense of awe. As you allow your own awareness to gently fade, you can connect the great cosmic darkness with the small, personal, and healing darkness of sleep. Just as the universe is mostly a quiet, structuring darkness, so too is sleep a journey into the quiet, restorative darkness of your own mind. Let the great, silent ocean of the cosmos be your final thought, a comforting, all-encompassing presence to hold you as you drift away. Thank you for joining me on this journey into the invisible world. It has been a true honor to share this story with you. If you have enjoyed our time together and found a measure of peace or wonder in these words, please consider leaving a kind comment below to share your experience. Your support in the form of a like and a subscription to this channel allows these stories to continue. I wish you the most peaceful, the most serene, and the most restorative of sleep. Good night.